Sampling error, the need for sampling distributions. Sampling error. Sampling error is the error resulting from using a sample to estimate a population characteristic. Sample distribution of the sample mean. For a variable x and a given sample size, the distribution of the variable x bar is called the sampling distribution of the sample mean. In statistics, the following terms and phrases are synonymous. Sampling distribution of the sample mean. Distribution of the variable x bar, or sample mean. Distribution of all possible sample means of a given sample size. Sample size and sampling error. The larger the sample size, the smaller the sampling error tends to be in estimating a population mean, mu, by a sample mean, x bar. Example: find the probability expressed as a percent that the sample mean will be within 2 points of the population mean. The test scores of 5 students are under consideration. The following is a dot plot for the sampling distribution of the sample mean for samples of size 2. So our number line goes from 69 to 87. We have dots over 70, 73, 75, 76, 2 over 78, 1 over 80, 81, 83, and 86. The population mean is marked as 78. To find the probability that the sample mean will be within 2 points of the population mean, we first need to figure out what 2 points represents. If 78 is the mean, 2 numbers to the left would be 76 and 2 numbers to the right would be 80. We have 10 dots, and within 2 points of the population mean, we have 4 dots. To find that probability, we have 4 divided by 10, which is 0.4, which gives us 40%. So there's a 40% probability that the sample mean will be within 2 points of the population mean. Example: for the population below, find the mean of the variable. Our population is 2, 4, 6, 8. To find the mean, what we want to do is add up our data and divide by the number of data points, which is 4. 2 plus 4 plus 6 plus 8 is 20. 20 divided by 4 is 5. So our population mean is 5. Example: for each of the possible sample sizes, construct a table with all possible samples and their sample means and draw a dot plot for the sampling distribution of the sample mean. Our data is 2, 4, 6, and 8. Find the sample mean x bar for each possible sample size n equals 1. Create a table with 2 columns. The first column is sample, the second column is x bar. The sample taken will go in the left column. Find the mean of that sample and put the result in the right column. Our possible samples will be, based on our data set, 2, or 4, or 6, or 8. To find the mean, we add up our data and divide by the number of data points. Since our sample is 2 and our sample size is 1, we have 2 divided by 1, which equals 2. Our next sample is 4, which is 1 data point. 4 divided by 1 equals 4. Our next sample is 6, which is 1 data point. 6 divided by 1 equals 6. Our next sample is 8, which is 1 data point. 8 divided by 1 equals 8. Our mean for our first sample is 2, our second sample is 4, our third sample is 6, and our fourth sample is 8. We draw our number line from 1 to 9 representing our mean, and then we put dots over 2, 4, 6, and 8. Continuing the example, find the sample mean x bar for each possible sample size n equals 2. We are still using our data set of 2, 4, 6, 8. Create a table with two columns. The first column is sample, the second column is x bar. The sample taken will go in the left column. Find the mean of that sample and put the result in the right column. Each sample has a size of 2, so I'm going to pick two numbers. 2 and 4, 2 and 6, 2 and 8, 4 and 6, 4 and 8, 6 and 8. Order doesn't matter, so a sample of 2, 4 is the same as a sample of 4, 2. And now we want to find the mean. For our first sample, 2 and 4, we have two data points, so we want to add 2 and 4, which is 6, divided by 2 gives us 3. For our sample 2, 6, we have two data points. 2 plus 6 is 8, divided by 2 equals 4. 2 and 8, we again have two data points. 2 plus 8 is 10, divided by 2 equals 5. 4 and 6 are two data points. 4 plus 6 is 10, divided by 2 is 5. 4 and 8 are two data points. 4 plus 8 is 12, divided by 2 is 6. 6 and 8 are two data points. 6 plus 8 is 14, divided by 2 is 7. So we now have a table of each sample and its mean. Again, we have a number line from 1 to 9 representing our sample mean. We have 1 dot over 3, 1 dot over 4, 2 over 5, 1 over 6, and 1 over 7. Continuing the example, find the sample mean, x bar, for each possible sample size of n equals 3. This time we want to pick three numbers out of our population. So we have our table, sample and x. One of our samples is 2, 4, 6, another 2, 4, 8, then 2, 6, 8, then 4, 6, 8. So this time we have three data points each. When I find the mean for my first sample, I have 2 plus 4 plus 6, which is 12, divided by 3 equals 4. My second sample, 2 plus 4 plus 8, which is 14, divided by 3, which gives us 4.67. My third sample, I have 2 plus 6 plus 8, which is 16, divided by 3, which gives us 5.33. My last sample is 4 plus 6 plus 8, which is 18, divided by 3, which is 6. Now I have my table of each sample and the mean. I draw my number line, again labeling from 1 to 9, and I put my dots. I have a dot over 4. I have one really close to 5, which is 4.67. One a little to the right of 5, which is 5.33, and a dot over 6. Continuing with the example, find the sample mean, x bar, for each possible sample size, n equals 4. So I set up my table, my sample, and the mean. In this case, since I have a population 4, there's only one sample I can take, which is 2, 4, 6, and 8. To find the mean, I add up my four data points. 2 plus 4 plus 6 plus 8 is 20. Divide by the number of data points 4, and that gives me 5. So I have my table with my sample and the mean, 5. Creating my number line from 1 to 9, I just have a dot over 5. Continuing our example, use the dot plots to create one plot with the sampling distributions for each sample size and interpret the results. Again, my population is 2, 4, 6, 8, and the mean of the population is 5. So I combine all of my dot plots. I have my number bar 1, 2, 3, 4, 5, 6, 7, 8, 9. At the top, I have the dot plot when n equaled 1. Below that, I have the dot plot for when n equaled 2. Below that, the dot plot for n equals 3. And below that, the dot plot for n equals 4. Then I have a dotted line tracking my population mean, 5. When the sample size was 1, we had no dots at 5. When the sample size was 2, we had 2 dots at 5, but the rest of the data was spread out. When we had the sample size of 3, the dots were much closer to 5, but I didn't have a mean of 5. And then when n equaled 4, our mean was 5. As the sample size increases, the sampling distribution of the sample mean clusters closer to the population mean. Continuing our example, for each of the possible sample sizes, find the probability that the sample mean will equal the population mean. We have our graph of the dot plots. In order to do this, we need to make a table where we have n, then the sample means, then the probability that the sample mean equals 5. Our sample sizes were 1, 2, 3, and 4. Then copying the sample means from our previous tables, for n equals 1, we had the sample mean of 2, 4, 6, and 8. When n equaled 2, we had the sample mean of 3, 4, 5, 5, 6, and 7. When we had n equals 3, our sample means were 4, 4.67, 5.33, and 6. When n equaled 4, we had a sample mean of 5. So starting with n equals 1, we want to find the probability that the mean equaled 5. Looking at the sample means, I have 4 means, 2, 4, 6, and 8. And of those 4 means, none of them are 5. I have 0 divided by 4, which equals 0. So if n equals 1, the probability that the sample mean will equal 5 is 0. Looking at n equals 2, I have 6 sample means, 3, 4, 5, 5, 6, and 7. And 2 of them are 5. So to find the probability, I have 2 divided by 6, which is 1/3. So the probability that the mean equals 5 is 1/3. Moving to n equals 3, I have 4 means, 4, 4.67, 5.33, and 6. None of them are 5, so I have 0 divided by 4, which is 0. So the probability that the mean equals 5 for n equals 3 is 0. For n equals 4, I have 1 mean, and it is 5. So that probability is 1 divided by 1, which is 1. So the probability that the sample mean will equal 5 when n equals 4 is 1. Continuing our example, for each of the possible sample sizes, find the probability that the sampling error made in estimating the population mean by the sample mean will be 0.5 or less in magnitude. That is, that the absolute value of the difference between the sample mean and the population mean is at most 0.5. So we start with our table where we have our sample size n and our sample means that we found earlier. For n equals 1, we have the means of 2, 4, 6, and 8. N equals 2, 3, 4, 5, 5, 6, 7, n equals 3, 4, 4.67, 5.3, 6, n equals 4 is 5. The population mean is 5. 5 minus 0.5 is 4.5, and 5 plus 0.5 is 5.5. The estimate can be between 4.5 and 5.5. We are looking for the probability 4.5 is less than or equal to the sample mean, less than or equal to 5.5. So I'm looking at n equals 1, and I want to find how many of the means fall in that range. I have 2, 4, 6, and 8. None of those numbers fall in the range of 4.5 to 5.5. So again, I have a probability of 0 divided by 4, which is 0. When n equals 2, I have 3, 4, 5, 5, 6, and 7. I have two means that fall between 4.5 and 5.5, so I have 2 out of the 6, which is a probability of 1/3. Looking at n equals 3, I have 4, 4.67, 5.3, and 6. 2 of my means fall in the range of 4.5 to 5.5 out of 4 data points. So I have a probability of 2 divided by 4, which is 1/2. So the probability is 1/2. For 4, I have 5, which falls in the range of 4.5 to 5.5. I have 1 data point out of a total of 1, which gives me a probability of 1. To recap the section Sampling Error and the Need for Sampling Distributions, the sampling error is the error resulting from using a sample to estimate a population characteristics. Sample size and sampling error. The larger the sample size, the smaller the sampling error tends to be in estimating the population mean mu by the sample mean x bar.